All right, we can get started. We have our seventh speaker of the summer. Pranjal has come in for the Summer of Data seminar talk. He is a PhD student at LTI in CMU who works with Sean Welleck. He's been doing a lot of exciting work across reasoning, formal code, and most recently around computer use agents. I know a lot of us have seen the L1 paper back in the day, and now his since interest moved towards uh, how to make better computer use agents. So he'll be talking a little bit about his most recent works and what he's excited about.
Cool. So I'll get started. So hi everyone, I'm Pranjal. Thanks Pratish for introducing me. So today I was thinking about talking about this work called Gym Anything. The title is Turn Any Software into an Agent Environment. This was the work done by me in collaboration with Pram and Sean at CMU. And I think at the core, the idea is basically how can you create environments or simulations using AI agents and train the models on them and improve your models. This work is specifically focused on computer use agents. So before we even go on to this work, I want to ask a very simple question. Or maybe you guys should think about it. What do you really think about computer use agents? If I use the term computer use agents, what's the first thing that comes to mind? And I mean, when I say computer use agents, I'm specifically talking about GUI agents. That's like agents that can look at your screen and take keyboard and mouse actions. What's the first thing that comes to your mind?
Credit card fraud.
Oh, mine's data set. Very different.
Yeah, so I tried this thing around a year ago. I asked some of my friends, and I think the most common answers were basically around this thing, like booking a flight, changing something in my Mac OS, or like filling a web form. But the way I see computer use agents is that it's about everything that humans do on a digital screen. So people are using computers like for all sorts of things. Personal use is fine, but there's also like lots of economically valuable domains and industries where people are doing digital work. So the examples would include like 3D modeling and design, astronomy and space, cybersecurity, DevOps, education, engineering, enterprise, finance, remote sensing, human resources, medicine, healthcare, robotics, and basically the list keeps going on, science and research and so on. And I feel like coding agents are great. We still need them, but they have been more focused on student kind of stuff rather than like this large scale of economically valuable domains. And why do we want to do that? Because of course, like it's economically really valuable. These occupations represent trillions of dollars in GDP. So what's actually stopping us from doing that? So the biggest problem that we have with computer use agents is we don't have data for training. So at least in academia, these are like some of the popular benchmarks. So all of these are benchmarks. There's no training data. Like OS World, probably you guys would have heard of it. It's like 369 tasks, just 9 software applications like Chrome or like some email client. And the situation, at least in academia, is so dire that like people were training on subset of benchmarks and evaluating on the other subset. That's the norm because you don't have the data. And the reason you don't have the data is because environment creation for these software or like basically for computer use is really hard. So OS World, like from this is a quote from their paper, they have 1800 hours of expert effort to create 369 tasks across 9,000. So naturally, it's not really scalable. So that's why I've been working on this thing called Gym Anything. And the idea is that you have some automated method using AI coding agents, AI computer use agents that would convert any software that you can imagine on like website that you can probably download, convert it into an agent environment. It will also create tasks for it. It will create verifiers so you can train your models. And that's what I'm going to talk about in this presentation. So I'm going to so the way this is going to be structured is I'm going to talk about 5 things. First thing is like what should we actually aim for, like when we are developing computer use agents. Second is like briefly about like having a good infrastructure for computer use agent is important. So what we built and what you can use if you are interested. Then I'll actually talk about how do we create these environments and how do we create these tasks. And finally, what all you can do with these created RL environments or SF environments for distillation. What are the results and those kind of things. So I'll start with the first thing, like what do we need computer use agents for? So what software applications should we train these models on? And our idea was very simple, that we will prioritize those softwares that drives the most economic activity. So we looked at some of the survey data, like the HostNet database. And there are like some other things like how much money like a specific occupation makes, and how many people they are in that specific occupation, what are different industries and everything. So we had some kind of filtering as well. Like, so for example, we cannot create environments for licensed software applications. But eventually we, based on our compute budget, we chose 200 different software. And just to give you an idea, it's not only like the highest economically driving, it's like more about coverage. So for example, if someone is doing cancer research, probably their representation in the economy is very small, but I would argue that their impact is much higher. So we have this like idea of like, ensuring diversity, ensuring high coverage by looking at STEM and research, looking at like different occupations, different domains, and ensuring that at least some representation is there in the 200.
So for economic core, like would that be stuff like, like pricing models, like, like sort of financial services stuff, and, accounting, sort of like, is it purely sort of like financial economic kind of things, or like, can you just give a few examples?
Yeah. I think the most common one was like spreadsheet. The second most common one was like PowerPoint, because like it's something that everyone uses, right? So everyone gets some kind of representation. Then you have some medical, I don't know what's the name for that, but like medical management, like EMRs kind of software. And then like finance and accounting. So that was the first step. So obviously, like based on your requirements, like if you're a practitioner, you could obviously change this. But we decided to go with some this strategy. The second thing is like how do we handle infrastructure? So the thing with computer use agents is that these agents should be running on different kind of operating systems. These would be having like different services. This would be like having different complex resource management. Some require GPUs, some require more CPUs, some require more RAM, all those kind of things. And it's just very hard to just scale that up like infra-wise. So we basically created this library, which is like kind of an abstraction. It just abstracts away everything that you do, like all the Docker, VM management, all of these things are abstracted. What you actually do for creating an environment is that you define it as a coding task. So an environment, let's say you want to install some EMR software, it's like you would require some kind of setup scripts. So download the software, accept the agreements and all those kind of things. There's task scripts such as like downloading the data, preparing the data for like, so that you can create the task with something that you can evaluate your agent on. Configuration files like management of resources, permissions, those kind of things. And you have this abstraction at the back, like it could run on like distributed machines, different kind of machines. You could parallelize it, logging, and all those kind of things are provided. So if anyone decides to do computer use agent, just to give it a look, I think it makes it a lot more easier and removes the engineering aspect from the computer use research. Now I'll come to actually like how do we create these environments part. And I think creating a computer use environment, the way we thought about it is itself a coding and computer use agent task. So let's take a software like spreadsheet, and the task now is like create this environment, create spreadsheet. Create an environment for this spreadsheet app. Now, just to clarify, when I'm talking about creating an environment, I do not mean creating a clone of the software. I mean downloading it, sort of setting it up, maybe running services, or just make it accessible to the agent that will be evaluated on that environment. But this is a coding and computer use agent task. So basically, we had just like 3 components in our pipeline. So one is the creation agent that basically it's a coding agent that actually tries to create the environment. There's an audit agent that's basically adversarial. I'll talk more about it. But its goal is to make sure that the environment is actually set up correctly based on the standards that we have decided. The third component is memory. So this creation agent needs to have some sort of memory that evolves over time, because like lots of software applications. So for example, in the spreadsheets, you could have Excel, you could have Sheets, you could have like some Linux-based spreadsheet softwares, or you could have a PowerPoint app that's from the same like company. So they're like common themes that the coding agents discover by actually executing code. So that gets saved in the memory. But yeah, now I'm going to talk about like
the creation agent already has the GUI as a code when it starts. Right?
Yeah. So the creation agent is basically it's a coding agent and it's a computer use agent. It has a computer use agent too.
So someone else did the conversion from GUI to code, or?
Yeah, I mean it's like a simple Python wrapper.
I see. They already.
Yeah. I wrote. Yeah. So it's a Python wrapper. And yeah, so maybe I'll just show the loop clearly. So the way it works is that I give a software name. Let's say I have a software name in mind. I give it to the creator agent. Let's say Cloud Code. It tries to build the software. While building, it can like interact with the infrastructure that I talked about, the library for spawning computer use VMs, as well as the code base. And its sole job is to set the environment up to the standards that I have given in the checklist. Now, we initially tried this, and this was actually working terribly bad. And the reason was that the model would claim that the environment is set up when it's not. Maybe it didn't verify things. Maybe there were like some loopholes. Maybe it was using placeholder data, and all those sorts of things were happening. So we came up with this like very simple idea where we said, all right, you set up an environment, that's fine, but you also have to provide a proof of evidence that the environment is set up. So let's say you need to have screenshots. So let's say I want to set up a EMR software, then I need to find a screenshot that this software is like open in my VM. It is running the required data and all those kind of things. Or maybe you need to provide logs that it actually worked out. But I'm not going to manually verify, obviously, because the whole goal is to generate environments automatically. So we introduce audit agent, which is again, it's a Claude code instance again running. But now the goal for this agent is to find mistakes. It is to find issues with these evidence logs. Maybe the evidence logs are not sufficient, or maybe the evidence logs point to something else. So what would often happen is that the application is never even open, and you don't have the screenshots. So that gets caught up. And this audit agent then provides an audit report that goes back to the creator agent, and it just continues. So at a high level, it's basically you have a creator agent whose goal is not only to set up an environment, but prove another agent that the environment is set up. And for the other agent, the goal is to find mistakes as much as possible. And you can keep continuing this loop, or you could like start up your iterations. But this really helped a lot in the held out sets that we were evaluating the environment creation on. I think probably skip that, but there's also this another component of memory that I briefly talked about. So what happens is that for every software that the
The audit agent, like how I assume it's given, some sort of like skill or some rubric by which to evaluate things. Like, what was the process for developing what the audit agent should do? Did you sort of have like an even outer loop of having the creator generate things, and you provided human feedback to the audit agent, and then like improve it sort of, the prompt, and then sort of iterate on that? Like, I'm curious, like at some point for all these things, like there's like some base case.
Right.
Usually like more opinion, but
yeah.
I'm curious, like where that was objective.
Yeah. So what we actually did initially was like of 200, we selected 5 software applications and we put it like on a handout.
Mm-hmm.
And the goal of this creator audit is to build those 5 environments every time it's new start. And it was more of me like prompting with Claude Code and figuring out where it's making a mistake and making a note of that.
Mm-hmm.
So every time you would like have a list of issues that you found, and then you try to condense them, and you try to create like as small summary of like checklist as possible that just covers everything. So that's more of me deciding like what those 6 things should be based on like how the performance on the 5 held out environments is changing.
Okay. Yeah. Awesome. Thank you.
I also think like generally like if it's a practitioner or someone, like maybe you could have like an expert in the loop, which is like this was like I decided the checklist and it stays the same for the next 200 software, but you could imagine that you could have like a human in the loop whose goal is like only after every software it looks at it and provides new feedback that just goes to the audit agent's checklist, not to the process. So that's like minimal input and maximum output improvements.
I guess one thing, and maybe we'll get to this, is that this whole process of converting any software into an environment, like do you set the goals of like what are the things that should get executed in the environment? Or is that all that the creator agent figures out itself? And like I guess in general, like when generating synthetic data, one of the questions, how do you make sure it's diverse enough? Or, like, I'm guessing there's some C tasks in the environment.
Right.
How do you like do all of that? Or is it automated?
Yeah. So first of all, everything's automated, but this is like a step-by-step process. So right now, I'm not even just talking about the task. I'm just talking about like software being converted into an environment. So over there, diversity is not that big of an issue. But as for like, I think that if your checklists are good enough, if you have like enough diversity of checklists that the model has to ensure, it does not have to be software specific, because there's like common principles that use real data and all those kind of things.
Good.
Yeah, but I will move on to the task. I'll come to the task shortly. Where we have a small trick to ensure diversity. I think generally it's a problem, but yeah, because of like this abstraction, hierarchical nature of like you have 200 software for every software you can create task. I think
So right now the goal is to convert the software into something where an agent can play and it's highly faithful to what the software should do.
That's perfect. Yeah. Cool. Yeah. So we also had this like idea of memory. So every so for the idea is that every time the agent creates a software, it would have like it's a coding agent. So it would have faced some issues and all those kind of things. It can write it down in like file storage, and it can write like software specific notes. Problem is that it grows up really quick because it writes a lot, and there's these common patterns that come in across software applications. So we use a summarization that takes the software specific notes and writes it down in general memory, and the creator agent is always told to like read the memory. Let's get this. So to give examples of like the 200 software applications, these are just 12 handpicked examples. So this one is like some home designing software. We have to like develop some home. This one is some astronomy software. This is I guess some protein folding. This is Blender. This is flight simulator and Google Earth. This is drone mission planning. This is health imaging. But basically the idea is that you have all these software that people are actually using, and you're able to at least sandbox them, like set them up with something realistic, set up services. Now I'll come to the task. So once you have a software sandboxed which an agent can interact with, how do you create tasks? So before even moving to that, I think task basically means has three different components. One is just the task description. So that's the goal that the computer use agent has to execute in the environment. The second is the environment instantiation itself. So every task can be different. So it can have like different data. It could have like different services. It could have a different settings. So that's like the part of environment. And the third is verifier, because you want to make sure that the task is actually completed successfully. So you can again have different kind of checks like programmatic, VLM-based checklists, etc. So now I'm going to talk about how do we create these tasks. So the idea that we call it propose and amplify. The idea is that how can we create diverse, like the question is like how can we create a diverse realistic tasks at scale. So the way it works is for every software, we first generate 5 seed tasks. And the way these seed tasks are generated is because we initially started from the OSTARnet database, we have the kind of activities, that specific occupation. So for every software, we have a mapping of like what occupations are using the software, what industries are using the software. And we provide that information to these models and ask it to pick something from them. So we use that. It's again an agentic loop where the agent tries to create the task, and there are some checklist-based guidelines like it should be real, it should be typical, it should be diverse, and all those things. But this is just like 5 seeds that is grounded on the OSTARnet databases. So what this ensures is that the tasks are actually diverse, because it's just 5 and you are grounded on some like real data. The problem with this is like this is super expensive, because like for every task you have to like use a full coding agent, and this is not really scalable. So what we did instead was we use now a non-agentic LLM that takes this 5 set of seed tasks as exemplars and tries to create more tasks. This non-agentic LLM still has web search, so it can look for different kinds of thing. Sorry, and then we have like this kind of automatic filtering where if the task like doesn't even set up, or like the computer use agent sees that there's nothing to even solve, then those kind of tasks are filtered out. But yeah, that's the main idea of ensuring diversity. There's a small trick that we do for the amplify agent, because like non-agentic LLMs would always output the same thing again and again if your seed is same. So we instead of making it parallel, we make it sequential. So anytime it creates a task, it goes back to the context, and it is told not to copy it, like similar. And then you have another check that ensures that the generated task is not similar to any of the 75 or the K tasks that you have created. But yeah, coming back to the diversity question, I think the main point is that because we have this hierarchical nature of like 200 software application, and then we have this like 5 seeds, which is grounded on the OSTARnet database, which already has like for every occupation the kind of activities they do. And then we have this like thing. The diversity is by and large decent enough.
Like I saw one of the software tools there was about video creation or something. So like if I just open iMovie, it's like
Yeah, that's the first thing.
there's like so many things that I could do. Right, I could like split a video like 3 times and then join them. Like there's like so much granularity in the task, but I feel like that's probably really hard to capture.
Yeah. I think like the next step for this, like if you want to ensure diversity, is like actually computer use agents moving across the software and figuring out things. That will like at least give you something more diversely rounded. So like every scheme is kind of different.
Yeah.
So you can like figure out, oh, there's this option in this menu then.
Like based on logs from your
current,
what are things they actually encountered.
Right.
Like I was seeing the drop down over there on the file. The GIFs, and it was like quite comprehensive, right?
Right.
Types of things that.
Yeah. We do a small version of that, like I'll talk about it briefly. But I think that's like the next step. So initially before Gym anything, I feel like we were training on benchmarks. Now we have at least 12,000 tasks across 200 software applications. We have train splits, test splits, we did some contamination filtering and those kind of things to do that. And everything is open source. So now I feel like you can do research on computer use agents with these data.
Actually, I have one more question. How do you know that the task can actually be solved?
That is not guaranteed, yes. Yeah. That is not guaranteed. But what we know is like, so it was interesting. Like when I initially released it, I was a bit worried that, maybe they're not solvable. So I took a subset of 20 examples. And I think for the hard set, I got like, I was able to solve 11 of them. I was like, okay, 11 of them, I can do that. And with the recent Fable model release, I think it was able to do 13 or 14. So, so I feel like we at least know it's 70% correct because the model is able to do that. The recent one. But of course, there's no guarantee that all of them would be solvable.
And when you say verified, what is verified?
Great question. I'll have to think about it. Probably it's a wrong term.
I think.
Let me remove it.
Do you have an example of one of the tasks?
Oh yeah. I was going to show you next.
Wait, sorry. One more question. How much variance across seeds do you get? Like, is it like some just totally fail? Like,
for this part?
Yes.
See the real data that.
I see. I thought this was like measuring stochasticity of some kind. Thank you.
Yeah.
Did you do that? Like if you give this exact same task, like given that the outcomes are non-deterministic, like do most of them, get consistent outcomes, or like are there some tasks, or there's some of these softwares that are like much harder?
I mean there are definitely some software that are much harder. The thing is that it's kind of difficult to scale based on just the task success rate because the tasks themselves would be harder or easier.
Mm-hmm.
So, I mean, in general, like softwares that require 3D manipulation, like CAD or Blender, the models are really terrible. Even Fable is terrible so far.
That's a good research signal.
Yeah, but they are improving very fast. So.
Do like all the tasks start from like the same place or like the same starting point?
Not really. No, it's all different. So so the way it works is that for every task you have a setup script. And the setup scripts define like maybe you want to install software or maybe you want to put it through some specific screen state or maybe some data or maybe services. But it's like a coding script that runs for each task.
I see. So for like long horizon tasks, have you like thought about like splitting it up into like multiple segments and then using that as like
I think we haven't really done that. I feel like we would probably need to do it at some point because at least for the open source models, like long horizon tasks are like really hard. It's also unclear like how much distillation performance you would get versus like making it easier. But
actually maybe from this 12,000 you can make another like set of like I don't know, even exponentiate it by taking midpoints of successful trajectories and then giving it to a simple model.
Right.
But they probably never even see that part of training at all. Never reach that, right? Like the more details, right?
Yeah, one interesting experiment that we had, I don't know because I didn't do like very extensively, was that even if you like truncate the trajectory at 50 steps and train the model, like a smaller model, like very small, like 2B versus like the teacher being Kimmy, for instance, that performs as well as like giving the whole trajectory. So probably the model is still like the smaller model is still learning like grounding and those kind of things, which is very well. But yeah, so maybe I can show an example of sample task. This is obviously cherry picked, so this is a good example. But the task is basically you have this camera surveillance software and there's a live stream running, and you have to identify if and when robbery takes place in this live stream. So the thing is like, if you want to really create this task, there are so many questions. Like, how do you set up a real camera? Like, how do you set up a real live feed, right? Where do I get this video feed from? And how do I even know if the agent actually solved the task correctly or not? So for this specific task, this is how it works. So we have this software called NX Witness VMs. So the model downloaded and everything. Then it downloads an existing public dataset on video surveillance. So that's like some academic dataset. It creates a fake camera stream, so like basically a digital driver that takes the video and injects it into the software as if it's a live stream. And finally, as to like how to ensure that the task was actually solved correctly or not, because it's a public data set, because the answer is known, the ground truth is in the data set. Now, the important part about it is that when we are evaluating, we are not evaluating only on the outcome, but on the process as well. So the model actually has to use the software. It cannot do guessing or it cannot do web search to arrive at the answer. Yeah, that's the idea. And this is like a sample task.
So typically, NX Witness is the environment.
Yeah.
And for that environment, one task,
It's
the
this.
agent came up with this.
Yeah, this task.
Was it part of the seed or the?
It was the seed of this. Yeah.
It looks like a very like.
Yeah, this is cherry picked.
I feel like an agent thinking about it like
Right.
in themselves would be like pretty cool.
Yeah.
But that's how you see.
Yeah. But I feel like even in the seed task, like just figuring out that, oh, you have to do a fake camera scene, because that's not in the OStarNet, right?
Okay.
What's in OStarNet is probably like, monitoring cameras and those kind of things. But then it decided to do all this.
Cool that it gets to like.
Yeah, exactly.
Also like realizing that the ground truth does exist.
Right. I think ground truth was like a common theme. So maybe I'll just give more examples. So the question is like, how do we do verification? So what we decided up, like after some ablations, is just use VLM checklist with this privileged information idea. So in the previous example, privileged information was the ground truth of like when the robbery takes place. But it's basically the agent that is creating this VLM checklist has access to the full setup script and everything. So it also knows where the data was downloaded from. It can like go to that specific website and try to figure out the correct thing. So another example is this astronomy software task where you have like this some star in some place, and you have to identify some planet transition. But the planet was actually discovered in 2017, so you already know what's the transit depth and all those kind of things. The VLM checks not only whether the final answer was correct, but whether the model actually used the software to arrive at the correct answer. We also have these like integrity checks, where the idea is that if let's say model searches for the answer online, that is not allowed. It has to actually use the software. We did some human ablations, like it was me basically doing a blind test. Blind test comparing like programmatic verifiers and VLM checklist. Apparently, VLM checklist turned out to be the best because it's kind of less work for the model. In programmatic verifiers, it would all like if you're generating automatically, there's no guarantee that it's correct. Maybe it's like it had more false positives, false negatives than things. So yeah, this is what worked out to be the best. Yeah, if anyone wants to look at the task and software, there's a QR code. Please feel free to take a look. You can also search it after you. But yeah, this is what we have. We have like I think by and large compared to any benchmark or any data set on computer use, more number of software, more number of tasks, high occupational coverage, and different operating systems. Okay, so this is probably something that you guys already do in like different settings. But I just my insights from like working on this project. This is like a lot of data work and manually looking through data and trying out different equations. And I feel like the most important thing is like spending more compute wherever you can, like even in the environment creation. Like if you just increase the creation audit loop, the number of iterations, it's like every time there's something new, and that feels like something more realistic. Obviously, there's like at some point it's going to saturate and it's not going to be that meaningful, but at least 5 iterations. And we can like use agentic models for task creation. Like we had this propose an amplifier where the amplify step was an LLM, not an agent. Maybe you can use an agent there. So in like any part of the pipeline, if you can just increase the computing time. AI agents are not trustworthy, obviously, but I found that the evidence thing really helped a lot. And having an adversarial agent like just removed me also out of the loop. So that was good. And yeah, spend time on making checklists. I had to iterate a lot. So if you have good checklists, I think that helps a lot. So, so
I guess one thing, do you think one other thing we could also think of is using diverse agents, like, for instance, like Pranjal and GPT?
Yeah.
They are stronger, or is that something you have intuition about? As compared to doing 5 rounds, do you think like doing this round with different agents?
Yeah, I actually initially tried with Codex and Claude. I felt like most of the, at least for the task creation, maybe for software creation is a different story. They were not like doing a lot different. I also like tried Gemini. Like all of them, like for whatever reason, had a similar flavor. So at least there's less diversity.
Everyone's buying data from the same.
Probably, probably.
Yeah.
So that's there. But yeah, maybe it could help. Like maybe having a different audit agent. So generally, I've seen like Codex is a better audit agent than Claude. So maybe we could figure that combinations out. Like
Yeah.
and see. Cool. So now we have all these environments, but what good are they for? So we do two kind of tests. One is evaluation, like can we evaluate models and see where the frontier performance lies, and the other is train. So we have these two splits. One is the 2-hour test, that's like 20% of the 12,000 tasks that we created. And there's this long split. This long split was basically, by long I mean long horizon split. The idea over here was that we ran Gemini and Kimi models on these like 8,000 tasks, the training task. And then we used another agent to figure out where the model is failing and try to create tasks that, where the model fails. And then I manually verified 200 of those tasks to make sure at least they're set up correctly. I don't really know if they're solvable or not. Now I know that most of them are. But yeah, that's what we did. So I'll be evaluating these models on these two splits. And the second part is training. So we actually tried different. So doing RL is like really hard. We have a small experiment, but we primarily relied on our distillation. So we tried different teachers like Kimi, Opus, Gemini. Interestingly, like Opus was by and large like the best model, but Kimi was the best teacher. And I feel like that's because you have the chain of thoughts available in Kimi. So that might be the reason. So we decided to just go with Kimi. So we just have like 2,000 correct trajectories across like all those 8,000 tasks. And we just will like these 3 different models from 2B, 9B, and 35B. The last one is MOE. So this is the result. So initially, I'll be just evaluating on the test split. So we have a train split and a test split. We have this like very strong LLM-based contamination filtering to ensure that no two similar tasks are present in the same split. And we were basically more, what's the right word? Conservative. Basically, yeah. Even if like they are not similar, we try to just split them to make sure like there's no contamination. So the TLDR is that compared to the teacher, at least the 2B model is like much worse. But it improves by a lot. So like 1.6 to 4.4, and kind of similar to Model 2X size. So we then tried like let's use a bigger model as a student model. So it almost reaches the teacher. I would believe like if you like increase the training or something, it might even increase it. But that was really helpful. This also points out like probably in future we can do some kind of rejection sampling. Just improve these models.
And it's an 8K trajectory.
Oh, this is 2K trajectory.
Just 2K.
Yeah, but with each trajectory is actually up to 200 steps. So there's like lots of tokens.
And each step is a different sequence.
Yeah. Because we have to summarize every steps.
Okay.
So this is just vanilla like next token.
Yeah, vanilla.
How much of this improvement do you think is from the fact that the data you are doing it on is relevant, and how much is just because you are, there's always some amount of like learning you get from a teacher regardless of what the domain is. Like if you distilled Communicate 2.5 into this model, but used a like unrelated or like, maybe just like generic code data instead of like these tool use traces, like, do you have any idea how much of an improvement you would get?
Yeah, I think so. This is going to be the last result, but like I was going to talk about like for the OS world, like that's a common benchmark. Like if you take the software applications there versus the software applications that we have. So on the OS world software applications, there's no improvement. Like in this scenario, the improvement was on these software applications that's like not common. So I feel like at least for distillation and at the small scale, it's important obviously to have something that the models are not already trained for. So I would not expect that like tool use like you would see a sudden jump or something, maybe on specific data distribution that you have. That's not, yeah.
Also, first word is old enough that's probably already in Coin 3.5.
Yeah, definitely. Some good results. So like we can obviously scale the number of training data. So we tried this thing. Okay, we have 200 software applications. We can do 50. We can do 25. We can do 100, and try to see how the performance improves if you reduce them, or if you reduce the number of tasks. Both of them show like standard scaling. This was also interesting. So I guess this is distillation, so not a general claim, but at least for distillation, the model was not generalizing to unseen software applications. So basically, we took like 25% of all software, that is 50, trained on those tasks for those 50 software applications. And then we saw that compared to training on all of them, you could recover 65% of the improvement. Or in other words, like compared to an untrained model, you can improve the performance. But when we evaluated on software that were not in the training data, the gap, like the improvement was like just 1 or 2%. So that basically points out to the fact that, at least for distillation, training on software specific data is important.
I want to go back to the slide before this. So you were mentioning how Opus was the best model, but thinking tests are probably useful.
Right.
So I guess there are 2 ways to test this. One, you remove thinking tests,
Yeah.
Kimi, and then train and see if it is much worse. Or alternately, like could you just take the generations from Opus, which is like a valid trajectory, and then generate thinking traces with like Kimi to fill in.
Right. So I did try the second experiment. So the problem with first experiment, I mean, you can do that. Definitely you can do that. But the format on which these models are trained on is that it's mostly in the thinking, and the action token is just the action. So you'll have to do some small counting. But the second question was, if you rewrite the thinking traces in some sense, right, like for Opus trajectories, I tried that. So the interesting part was that if you use a stronger model, the better it is. But it still doesn't beat like Opus, or at least I was not able to beat Opus. So this was a specific problem for Gemini Flash. If you train on those thinking traces, nothing happens. Like training simply was not happening, even though Gemini Flash is not that bad model. So I tried rewriting. I tried using the same model to rewrite. I used a like much larger model to rewrite. It was like clearly a much larger model. It's better. But
I guess we're having this discussion with Dhruva the other day that these artificially generated thinking traces are not faithful because they're like not causally thinking.
Yeah, right.
I guess that's probably
that's what my guess was also. And probably these there's also this thing like these summaries are also not causally, like the summaries that are generated for these thinking traces that you get from these API models is also like not causally related.
So,
I mean, is there strong evidence showing that like the degree to which thinking traces are causally relevant even for the model that's doing it? Like we know they're correlated with the outcomes, but like you guys are going and like manipulate what is being like the activations and the traces mid generation and see that it actually gets you substantially worse outcomes.
But I guess in his case, like artificially generated thinking traces don't really help. So I guess there's
there's like an intuitive reason. That's all.
Well, so here's like a sort of tangent question. Like if you took Kimi K2 and took away its thinking traces, but then had Kimi K2 try and recreate the thinking traces, how would those compare to the thinking traces that were actually generated in just like
it should be much worse if all of this discussion.
Yes.
I mean, isn't that like kind of what you do in self-distillation, where like you have the final outcome and you don't do another rollout, but you use that for log props. So, and that probably.
But like I said, you're trying to make it learn to think also.
Yeah, that's true.
It's learning something that's not really useful to make the final judgment. Sorry, I was stuck on that.
No, that's a good question. Yeah. Also with Gemini models, like some random tokens will have like a sudden high loss. So I don't really know what that was. So we also had this like long horizon split, and to show like how good that or how hard the split is. All these models, like if you give them maximum 500 steps, were terrible. So Gemini 3 Flash were 11.5. 6% for Sonnet, Kimi 2.5, and with GPT 5.4, if we give like the complete budget, that is like you can use whatever you want, it got 27.5%, but it costed like around $18 per trajectory. I do not think that's like what a human would take, definitely much less than that, but yeah. So there's that kind of gap as well. Now there's this new result with Fable. I evaluated on a small subset. It might get 70%, so we'll have to update the benchmark soon. But yeah, so it's there. Yeah, the other thing was like, can you scale the inference compute for like these computer use agents? And scaling inference compute here basically means that you stop after 50 steps, maybe 100 steps or 200, 500. So we did this thing with Gemini Flash and tried to see the performance. So there's like a steady increase in performance. So basically what this tells you like is that even after 500 steps, the model, if you like let it do something, it is able to get some performance improvement. Now, none of the tasks requires more than 500 steps. So it's mostly like it being slow, it being like taking multiple steps, it being stuck in loops and all those kind of things. But yeah, that's
I guess there's one element here that when humans interact with the software for the first time, we are still learning.
probably.
And it's probably still learning how to navigate the software.
Yeah.
And if it
that's
had
for
like
sure.
a memory mechanism, like use that and then do another round.
Right.
And probably do all of it in like much lesser steps, given everything it learned.
Yeah. Yeah, definitely. That's why I think like doing some kind of RL on this would be like very interesting because like instead of explicit memory mechanism, it might probably even learn it.
It's like on the fly learning.
Yeah. Like test time training.
Yes.
Yeah, and you can clearly see from the trajectories that it discovered something now. Like it tried 50 steps and then it discovered something. But the important thing is that it should not give up. So yeah. We also tried this like very naive thing. This is like not statistically significant result, but what we did was like whenever the model would stop, we would just reprompt it. We would go to another agent that would check the trajectory and see whether the task is completely solved or not, and just ask it to do it again. And it slightly bumped the performance. It's like, although it's funny that if I just like reprompt whenever it stops to you have not completed the task, you get a simpler bump as well.
Mm-hmm.
So there's like small gains that you can get just by trying to increase the inference compute.
Do you see these things with open models also because they're usually much more set long context?
That's a good question. I haven't really tried that. But an important point is that the context is actually not that long. It's maybe like 30,000 tokens because like we have to summarize really quick. So yeah, I think the obvious question is like, does RL training help? Now this is a very small experiment, and I don't have that much compute because like as I showed, like even GPT 5.4 costs like $18 per trajectory. If you really want to train a model now, it's very expensive. So I did some experiment. The results seem promising. It's the training curve. It's increasing. But at least on the test performance, we got like 4% score improvement, and pass rate also increased by like 2 or 3%. So this might actually be useful, like if you are a lab who wants to train models on computers. So now the question was like, okay, it's great that it works good on our benchmark by training on our data set, but what about the downstream benchmarks, right? So we tried OS World, and this was the 9B model, I think, and the performance was basically the same across, and we were like a bit worried, like probably there's something wrong with our data set, maybe it's like out of distribution or something. So we took the 9 software applications from OS World and then checked like for those specific software who are like in our Hua world, what is the performance? So actually, like after training, the performance was basically the same. So there was a huge jump when you are looking at all the 200 software, but not when you're looking at those 9 specific OS World software. So we thought maybe it's just because that these models are already trained. And also an important thing is because every software roughly had only 10 trajectories, I think that's not enough to put the models on the software. So the gains were coming more from software that the model has never seen. Rather than the existing ones. So we ran this specific experiment where I think I generated around 1,000 tasks or something per software, and collected lots of trajectories using a 9B model and tried to like do some kind of rejection fine tuning. So on 15,000 trajectories, we saw like 5% performance improvement on OS World. So, and again, we did all the contamination checks and everything. So it seems that it's improving. So I think the TLDR is like it's important to train on software, at least if you're distilling. And RL is possible, it seems promising. And increasing inference compute can also help because like the model can search and learn on the fly. So.
But also likely train on OS.
Yeah.
Actually,
Yeah.
It's good. Find Pinterest Palisade. Put the post training data in pre training.
it's
Yeah.
posting.
But cool, yeah. I think like in general, like this is a general recipe that you can like scale very much. Like if you want, like we have like 3,400 software selected, based on like how much compute we had with cloud code and everything. We decided to 200. You can increase that. You can increase the number of software tasks for software. You can generate more trajectories. You can have like this kind of improvement loop where like the model generates hardware tasks over time. And you can have like many steps for trajectories. So yeah, it's like just a ballpark number as to what you can do if you had to. Obviously, it's a question like whether, like at 48 trillion tokens, would you be able to get more performance improvement than 5 trillion tokens or like 500 billion? Because you have to ensure diversity. But yeah, it seems promising. Yeah. So I'll just end with like one more slide, and it's like, what do I think about like this GM anything idea? I think the way I'm thinking about, like especially for my PhD, is that like this might claim that creating simulations and environments is actually an easier task than optimally acting in those simulations. And computer use agent was one such example where the model created tasks and was not able to solve them. But I think that once we have these like coding agents that are like really getting better and better, they would be able to create more advanced simulations or environments of multiple agents, or maybe even like just robotics and those kind of things. And we would be able to train different types of models. I feel like the recipe, the 5-step recipe that we have in Gym Anything, I feel like you can probably extend it to robotics, video games, science, decision making. Coding is something I think people are already exploring, like endless terminals and other kind of works. But that's the goal, the main idea. Just like create more simulations, more environments. So try to make it as much automatically as possible and try to train your models. Cool. Yeah.